In a chemical system, if on average the bonds that are made during a reaction are stronger than the bonds that are broken in that reaction, then energy is released, and this enthalpy of reaction can be used to raise the temperature of the system and its surroundings. Let's use this information to calculate the final temperature after the reaction of magnesium nitride with water to form nitrogen, hydrogen, and magnesium oxide. We're going to start off with 15 grams of magnesium nitride and a kilogram of water that we hold at 300 Kelvin and a constant pressure, say atmospheric pressure. We know all the heat capacities and we know the enthalpies of formation of the system, so we can use this information to figure out the enthalpy change during the reaction. As always, we start with a balanced chemical reaction. And this reaction may look familiar. We've done this one before, actually. So we start off the same way, balanced chemical reaction, including all the phase designations, and then we're going to determine the limiting reagent, which is in this case the magnesium nitride. Much lower quantity of magnesium nitride compared to water, which is there in great excess. This allows us then to determine the final composition of the system. All the magnesium nitride reacts and is converted quantitatively to hydrogen and magnesium oxide and half as many moles of N2. The number of moles of water also decreases, but again we have a large excess of water in the final composition of the system. Knowing the composition, we can now determine the heat evolved by the reaction, but we'll need delta H for the reaction, right? And the way that we can calculate delta H for the reaction is by way of the delta H of formation, right? We know the stoichiometry of the reaction, and then we know that we can get delta H for the reaction by summing all of the delta H values of the products multiplied by their stoichiometric coefficient. And then we're going to subtract off all of the delta H of formation values from the reactants. Again, they have to be multiplied by their stoichiometric coefficients. In this case, we only had one that differed from plus or minus 1. That was that of nitrogen, which was 1/2. So we put that in there. Oh, wait a second. Yeah, delta H of formation, the delta H of formation of elements in their standard state is 0. And we have 2 of those elements here. N2 is in its standard state, H2 is an element in its standard state. Both of those have delta H of formation of 0 then. We sum up all the other terms, subtract off as appropriate, and we find delta H for the reaction, which is highly exothermic. If we now multiply by the number of moles that reacted, which was equal to the number of moles of the limiting reagent, magnesium nitride, then we determined that 227.2 kilojoules were released during the reaction, and of course the heat that's absorbed by the system is equal and opposite to the heat that was evolved from the reaction. That heat is then used to change the temperature, and we know that the heat evolved is equal to moles times heat capacity integrated over the change in temperature dt from the initial temperature to final temperature. We know the number of moles, that's a constant, we pull that out of the integral, and we're going to assume that the heat capacity is also constant, so we'll pull that out of the integral, so the heat evolved will just be number of moles times the heat capacity times delta T. But we have multiple components in our system, and therefore we've got to do a sum. The moles of each component times its heat capacity times delta T. And delta T, of course, is the same for each component because they're all in thermal contact with one another. Now let's solve that for delta T, the temperature increase in the system. We take the heat available from reaction, and then we divide through by that sum of moles times heat capacity for each component in the system. We've done this problem before, and we know that water is in large excess, so we don't have to worry about the contributions from all of these other components. So we can just consider the contribution from water, and we find a 54 K increase in temperature, delta T of plus 54 Kelvin, which when added to our initial temperature of 300 Kelvin means that the final temperature of the system will be 354 Kelvin. So we know the final state of the system in terms of both the composition and the final temperature, right? And it's good to use a large excess of solvent here because that allows us to dissipate this highly exothermic reaction. The heat that's evolved will be dissipated and we get a not too large temperature rise, right? What if we now change the amount of water and decrease it to only 150 grams? What final temperature will we get in this case? Well, the balanced chemical reaction is the same, and the limiting reagent will be the same. Also, the number of moles, the quantity of all these other components will be exactly the same as before, but of course the quantity of water is different, right? Just under 8 moles will be left after reaction. So we've got the final composition of the system with less water than the first example. Now we can determine the heat evolved. The heat evolved, well, it's going to be exactly the same as before because we have the same limiting reagent, the same amount of that reagent, and it's the same delta H for reaction. It's the same reaction. So we know, again, 227.2 kilojoules are available to heat the components after the reaction has gone to completion. And again, delta T is going to be that available heat divided by the sum over all of the components, that product of moles times heat capacity. We'll put the contribution from all of the components in here. So let's do that. We'll take the heat evolved, 227,200 joules, and divide through by all of the contributions here, which will give us a delta T of 354 Kelvin. We add that to the initial temperature of 300. That means the final temperature is 654 Kelvin. We should look at that number. Always look at your answers and see if they make sense. And this one should be obviously wrong. There's something wrong here. And what is wrong is, of course, that water evaporates at 373 Kelvin. And so we're going to start to evaporate. You can't get water to stay in the liquid phase at 600 plus Kelvin unless you have a huge pressure in the system, right? So water is going to start to boil. It only takes just under 47,000 joules to get the system to 373 Kelvin, right? As we add heat to the system, as long as no phase transition occurs, the temperature is going to go up. But as soon as we hit the boiling point of water, then the added heat that we put into the system is going to go into evaporating water. And during a phase change, the system stays isothermal. The temperature stays the same while water is available to boil. So what's going to happen is we're going to take out 46,880 joules to get the system to 373 Kelvin. We had 227,200 joules initially, so we subtract off the amount that got us to 373, and that amount of heat can now be used to boil the water. So you take that heat and you divide by the delta H of vaporization for water, and you can figure out how many moles of water you will evaporate. It'll be just over 4 moles of water, but we had about 8 moles originally. So if we take 7.932 moles of water that we have available in the system and we boil off 4.098 moles, that will leave 3.834 moles of water that remain as liquid water. And at the end of the reaction, you're going to have liquid water in equilibrium with its vapor. We didn't boil off all the water, so you know that the system will then have a final temperature that will be equal to the boiling point of water. Some of the water was boiled off, Some of it went into the gas phase. And the final temperature will be equal to the boiling point of water. Now, if we had reduced the amount of water, the quantity of water, below 4 moles, then we would have been able to boil off all the water and we would heat the system significantly above the boiling point of water. So again, a very good reason to perform reactions in large excess of solvent is to disperse the energy of an exothermic reaction so that you avoid large temperature rises, you avoid boiling, and you also avoid then, if you avoid boiling, you avoid the possibility of building up high pressures, because we don't want that to happen, as it could potentially be dangerous. You should always do the thermodynamics before you do any new reaction to make sure you keep the pressure and temperature in safe limits.